Today's problem is connected components. This is on Interview Bits. It's part of their 12-week interview preparation kit. And you can pause the video, go over there and try this problem, come back, and then we'll walk through the solution. Okay, so difficulty level on this is listed as easy. Okay. It's well, there's not a lot of ratings on this problem. 62 thumbs up, 27 thumbs down. I don't know if it's a relatively new question for them and they don't have a lot of ratings or not a lot of people attempt it. I think the percentage of thumbs down, it's pretty high. And I'm guessing that's because of the rating, easy. I don't think it's an easy problem. I mean, it's a graph problem, and you can get hired as a software engineer without encountering graph problems in your interviews, depending on what kind of job you're applying for. I mean, if you're doing business applications, I don't think you'll get graph questions, but you know, for if you're working, if you want to work at a tech company, graphs are pretty common data structures, you know, for representing networks, and so they're used a lot in web applications. Anyway, let's get to the problem description. We're given a graph with A nodes. Let me run that up here. All right, so the input A, the number of nodes in the graph, the edges in the graph are given in a 2D array. B, actually, for if you're using the Java template as we are, it's a list of lists. There is an undirected edge between B I0 and B I1. So B is a list of lists, and each nested list contains two integers. Wait a minute, is that, yeah, it contains two integers. And so there is an edge in the graph, an undirected edge between those two integers. Find the number of connected components in the given graph. Okay, connected components, by the way. A connected component in a graph is a set of vertices that are connected to each other. It's not required in a graph that all the vertices be connected to each other. So there may be multiple connected components in a graph. We'll see that in the examples. All right, problem constraints. A, number of nodes is somewhere between 1 and 10 to the 5th, 100,000. Length of B, so that would be the number of edges, also between 1 and 100,000. The vertices, which is, the vertices are numbered from 1 to possibly as high as A. I guess I shouldn't say possibly. I mean, like if A is 100, there's 100 nodes. What that's saying is that the nodes will be numbered from 1 to 100. That's a little bit unconventional. Usually we start the nodes, the numbering at 0 because it corresponds better to, you know, programming languages. But so that's good to know that they start with 1 so that we don't define our data structures as size A. Okay, input format. First argument is A. Second argument is in our case, a list of lists called B. Output format, return an integer, the number of connected components. All right, example. First example, A is 4. There's 4 vertices, and there's 2 edges. There's an edge from 1 to 2. There's an edge from 2 to 3. There's no edges to 4. So 1, 2, and 3 are connected, but 4 is not. So two connected components are 1, 2, 3, and 4 is by itself. All right, input 2. There are 3 vertices and 2 edges, 1, 2, and 2, 1. That's, well, you don't really have to say 1, 2, and 2, 1 because they're undirected edges. So an undirected edge from 1 to 2 also implies that there's an undirected edge from 2 to 1, but they're both in there. Okay, in any case, yeah, 3 is, there's no node, no edge to 3. So that's going to be, again, 2 connected components. All right. Different ways of doing this. You can do a breadth first search for connected components. You can do a depth first search for connected components. That's what we're going to do. You can do a union find, sometimes called a disjoint set for connected components. Disjoint, well, union find is not as commonly used. It's more for special cases when you're dynamically creating the graph. But yeah, we're going to use a depth first search. Let's look at our data structures here. For a depth first search, we have a marked array, which is going to indicate whether or not a vertex has been visited or not. We're going to have an ID array indicating that a vertex is in a particular component, and we're going to have a count. That's what we're going to return. We're going to count the number of connected components. All right, so here's the template that they give us. Solve. Now, you don't have to create a graph object. I think it's better to create a graph object, you know, to get comfortable with creating a simple graph object, and you know, you can modify it for other graph problems. I mean, the important thing is this list of lists, the way that we get the edges here is not useful, because if we wanted to see what vertices are adjacent to vertex V, the only way we could do that is to go through the whole list, go through every list in the list and see if we can find vertex V in there and see what it's connected to. We don't want to do that. There's a couple of common ways of representing a graph. One is an adjacency matrix, and probably the more common one, which we're going to use, is adjacency lists. So we're going to have a list of lists, but each list is going to correspond, the index of the list is going to correspond to a vertex number, and the elements in the list are going to correspond to the vertices that are adjacent to that vertex. So let's start here. Graph G equals graph A plus 1. We're going to pass in, well, okay. Let's look at the constructor for the graph object. All right, here's our adjacency list definition. Again, a list of lists. We pass in V, we create the adjacency list, and then we create from 0 to V an empty adjacency list. So we have a list of initially empty lists going from 0 to the number of vertices. All right, we iterate over the edge list B, and we call a method in G called add edge. We send in the 2 endpoints of the edge. What does add edge do? Add edge. It adds an edge. We'll call the vertices V and W. It adds an edge from V to W. That is, in our adjacency list, we get the list at index V and we add a W to it. We get the list at index W and we add a V to it. Again, it's an undirected edge, so it goes in both directions. We've got two arrays that we're going to use in the depth first search to find connected components. One is marked, whether a vertex has been visited and added to a component, and ID, what component is it in. All right, from V equals 1 to A plus 1. We're going to do the depth first search. If the vertex, for each vertex, if the vertex has not already been added to a component, we will do a depth first search on it to find out what vertices are connected to it. So here's the DFS. We'll set marked to true, meaning we're adding the vertex V to a component. The ID of V is going to be count as we increment the count for components. The next component, we will give that the number of the current count. And for every W in the adjacency list for V, if W is not already in a component, we'll do a recursive depth first search on W. Okay. Let's see. And for every vertex we find that is not already in a component, we will find all the vertices that are in the component with that vertex and increment the count. So we found another connected component. All right, am I leaving anything out here? I don't think so. Well, yeah, is that used up here? It is. Okay. Yeah, we do have a method here to return an adjacency list. Return the vertices adjacent to vertex V. So it's ADJ get V. We can send that. Back. All right. It should be it. Let's give it a try. All right. Thanks for watching. I hope this was helpful to you. If so, hit like, subscribe, check out the playlist on the screen to keep leveling up your interview skills. The video description and the pinned comment both have links to additional resources, including a free LeetCode patterns cheat sheet, which will include depth first search and breadth first search. You can download that immediately, and we'll see you next time.